Welcome to the hands-on workshop, Performance Optimization for Intel Xeon Phi Processors. This is episode 4. I am Andrei Vladimirov with Colfax International. In this episode, we will talk about the utilization of high bandwidth memory in Intel Xeon Phi processors of the second generation. If you have a bootable Knights Landing processor, it has access to two types of memory, on-platform and on-package. The on-platform memory lives on the system board in the form of standard DDR4 modules. It can be in the hundreds of gigabytes in size, and the bandwidth that it can deliver is over 90 gigabytes per second. The on-package memory is fused onto the chip. It is based on the MCDRAM technology. It is exactly 16 gigabytes in size, and the bandwidth that it can deliver is over 400 gigabytes per second. When I say high bandwidth memory, or HBM, and when I say MCDRAM, I mean the same thing, but HBM is the role of this memory in the chip organization, and MCDRAM is the technology. At boot time, you get to choose one of the three modes of operation of high bandwidth memory: flat, cache, or hybrid mode. In flat mode, the entire high bandwidth memory is exposed to the operating system as a NUMA node. It means that this memory is addressable, and you get a special allocator with which you can put certain objects in high bandwidth memory and other objects in on-platform memory. In cache mode, you do not see MCDRAM in the operating system. Rather, it sits quietly between the CPU and the on-platform memory, and the objects that you read from the on-platform memory get cached in high bandwidth memory. In hybrid mode, you split your high bandwidth memory, and one part of it is used as a cache, the other part remains addressable. There are pros and cons to every approach. Particularly in the flat mode, you get full control over what goes in high bandwidth memory, but you need to modify your code for that. In the cache mode, you automatically take advantage of high bandwidth memory, so you don't need to modify your code. But the drawback is that if you have misses in MCDRAM as cache, then these misses have twice as great a latency as simply access from CPU cores to the on-platform memory. We have this flowchart to help you decide whether you use flat or cache memory mode and how exactly you operate. And this is only applicable to bandwidth bound or bandwidth sensitive applications. If your application requires less than 16 gigabytes of memory, then you have a very interesting approach to run the entire program in high bandwidth memory. And for that, you will use the flat memory mode and a tool called NumaCTL, which I will illustrate in a few minutes. No code modification is required in this approach, but you have to be able to fit your application under 16 gigabytes. If your application requires more than 16 gigabytes, and you know exactly which objects are bandwidth critical, and you can partition out the bandwidth critical data containers and stage data for high bandwidth access, then again use the flat memory mode and use a special library called memkind to selectively allocate certain data containers to high bandwidth memory. You do have to modify your code in this case. And finally, if you don't know which objects are bandwidth critical in your application, then you simply use the cache mode. You do not modify your code, and you allow the chip to figure out at runtime how to use high bandwidth memory. Let's talk about the flat memory mode. In the flat memory mode, I can query the memory configuration of my system using the tool NumaCTL with the flag -h. It shows me two NUMA nodes, 0 and 1. Node number 0 shows me that the CPUs belonging to it are logical cores from 0 through 255, 256 logical processors in total, This is my 64 cores with 4-way hyperthreading. NUMA node 0 also contains all of the DDR4 memory that I have in my system, and I have 96 gigabytes of it. I also have NUMA node 1, which has no cores affiliated with it, and 16 gigabytes of memory. This is my high bandwidth memory. So that first approach that I promised, that is easy and requires no code modification, is to run the entire application in high bandwidth memory. I can do it using the same tool NumaCTL. I just have to type NumaCTL membind1 to bind it to NUMA node 1, and then the name of my executable. And the entire application is going to be executed in high bandwidth memory as long as my memory configuration is flat. If I want the second approach, where I use the memkind library to selectively allocate objects in high bandwidth memory, then in C and C++, I will include a header file for a convenient wrapper around the memkind called hbwmalloc. And this will give me access to a function hbwmalloc that allocates a buffer in high bandwidth memory. If I want allocation with alignment, then I can use hbw POSIX memoline, which takes 3 arguments. The reference to my pointer, the alignment value, and the buffer size. For objects allocated with these special allocators, I have to use a special deallocator, hbw-free. In Fortran, I can also selectively allocate in HBM. For that, I will need to use allocatable arrays declared with the attribute fastmem. When I call allocate, these arrays will go to high bandwidth memory. It is important that when I compile with Intel compilers or with GCC, whether I compile C or Fortran application, I need to use the flag lmemkind to link the memkind library at compile time. The memkind library is open source. It is available on GitHub at this URL. To learn more about using high bandwidth memory in Intel Xeon Phi processors, download this free publication or read online on Colfax Research. In episode 5 of this workshop, I will talk about one more boot time decision for Intel Xeon Phi processors, the choice of the clustering mode.